Welcome back, precalc students. We're going to go ahead and look at Chapter 1, Section 2, and we're going to look at functions. So pairs of quantities that are related to each other by some kind of rule of correspondence is called a relation. So anytime we have two variables that have a relationship to each other, we call a relation. So for example, we have the simple interest earned on an investment of $1,000 for a year is related to the annual interest rate R by the formula I equals 1,000 times R. Or the area of a circle is related to its radius by the formula A equals pi r squared. So the definition of a function is really just a relation from a group of numbers A to a group of numbers B that assigns each element in group A to exactly one element in group B. So if I put in one thing, I should get out one. Kind of like if a vending machine is working properly, I put in money, I get out one item. Not I put in money and I get out two items. If that happens, it's not functioning, and those people who own the vending machines lose money, and that's bad for the people who own the vending machines. And so for it to function properly, we need one from the domain, which is our input, to go to one in our range, which is our output. Now, our domain, one item in our domain could go to the same thing in the range. So Josh could put in money and get out Doritos. But Joe could put in money and get Doritos. So they can end up at the same spot, but I can't have Josh put in money and get Doritos and Twix. So we shouldn't have two different things coming. So how does that look? Well, we have a mapping here with three items in our domain. So it's a function if this can go to here, this can go to here, and then this goes to here. We're okay because each X only has one arrow, which is one output. Now where we go wrong is when this one has two outputs. So I have two arrows coming from it, which means two outputs. And so what would that look like if we were looking at points or coordinates? Well, if I put in a 1 and I get out a 5, but I put in a 1 and I get out a 3, this is one input, 1, with two outputs, 3 and 5. And that means it's not a function. So decide whether y is a function of x. Okay, so the input value x is the number of representatives from a set, and the output value of y is the number of senators. So let's look at Alaska, for instance. This is our representatives, and this is our senators. So in our representatives, we have right now Don Young, and then in our senators, we have Lisa Murkowski and Dan Sullivan. And so if we're representing, hey, I input this to get out the number of senators, it looks like that would not be a function. But if it was just the number, well, my one representative gives me out two senators, that would be a function. So depending on how you're looking at it, how you're mapping it, would be different. So let's look at our table. Is this a function? So let's look for any repetition in our input. And we do. We see repetition right here. When I put in the number 2, I get two outputs. So this makes it not a function. So this is no. This would be yes. And then very similar in graph C. So I'm looking at when I look at this x value -2, do I have two outputs, which would mean that I'd have two different points. And I don't, I have one. Well, let's look at this one. Looks like I only have one output. Let's look at this one, one output, one output. So for each x value or input, I only have one output. So this is a function. Now let's say I had an extra dot down here. If I had that, then it would not be an output, because not be a function, because now I have two outputs or two y values that go with that x. Okay, so our notation that we use, or our things that we use, is we use f of x. So typically, if we have y equals x squared, we could say y is a function of x. And when we say y is a function of x, then we're talking about this would be our input, this would be an output. Now, how can we tell if it's a function? Well, we could graph it, or we can kind of look at it and see if I put in something, will I end up with two outputs? And so here, if I solved my very first equation, I'm going to just move this over here, x squared plus y equals 1. So if I solve for y, so I can get that whole y equals, we get y equals negative x squared plus 1. And if I were to graph this, this would look like this. And so I know that if I do kind of that whole vertical line idea, looks like every single spot I'd only have one output. So this means that it is a function. But when I look at my next equation, negative x squared, or negative x plus y squared equals 1, if I solve for y here, and then I'd have to square root to get y by itself. Now remember, when I square root, I have to plus or minus. Now all of a sudden I get two outputs because I have a positive and I have a negative answer. So this is not a function. So we find that if we end up with something like a y squared or a y to the fourth, when I have to solve for y to be a function of x, it's not going to be a function because I'm going to end up with those plus minuses. So now that we know that something's a function, what do we do when we have solved for y? Well, we replace y with that function notation f at x. Now we don't always just use f, sometimes we do g, sometimes we do h, and every once in a while we'll do t, especially when we're dealing with time. And that means that, hey, if you see this, it's really a function. So we just replace y with our function notation. And then we have something like this that says f at 0. And since 0 is in the x spot, that's just saying, hey, find the value of my function when x is equal to 0. So all that means is that on this side, I'm going to plug in 0. So this would become 1 minus 0, because 3 times 0 is 0, and 1 minus 0 is 1. So if I'm trying to find f of 2, or f at 2, depending on how you want to hear it, then that just means that I'm going to plug in x equals 2. So this is 1 minus 3 times 2, so it becomes 1 minus 6, which is negative 5. And that's how I work with my function notation. So let's go ahead and look at a couple more problems. So now I have g of x is negative x squared plus 4x plus 1. Find g at 2. So that means I'm going to go ahead for g of 2, or at 2, negative, and in the x spot I'm going to put 2 squared plus 4 times 2 plus 1. And then I'm going to have negative, well, 2 squared is 4, so negative 4 plus 8 plus 1. 8 minus 4 is 4 plus 1 gives me 5. So my value when x equals 2 of the function is equal to 5. Okay, what about g of t? Love this one, because even though it looks complicated, all you're really doing for g of t is replacing x with t. So this would be negative t squared plus 4t plus 1. And that's it. That's all you have to do. Love it. But our last one, well, that's a little bit more complicated. So g of x plus 2, that means wherever there's an x, now I'm putting in the parentheses x plus 2. So this is negative x plus 2 squared plus 4 x plus 2 plus 1. So the very first thing I have to do is I have to do this x plus 2 squared. Now x plus 2 squared, you cannot distribute that exponent. That is really an x plus 2 times x plus 2. Which means I have to multiply, so x times x is x squared, x times 2 is 2x, Then I have to distribute this one, so 2 times x is 2x, 2 times 2 is 4, which really means that this is negative x squared plus 4x plus 4. So now I have to distribute the negative, which gives me negative x squared, negative 4x, negative 4. Here I have to distribute, so plus 4x plus 8 plus 1, which is a plus 4x plus 9. Luckily, the negative 4x and the positive 4x cancel, so I get negative x squared. 9 minus 4 is positive 5. So this is our g of x plus 2. So really just funky substitution and then remembering your rules of arithmetic. Can you distribute over addition, an exponent over addition? No. So then I have to FOIL it out. Okay, piecewise functions. So when we have a piecewise function, what we're going to go ahead and do is I'm going to go ahead and practice graphing it. So what we do is we graph this, but only when x is less than or equal to 0. So when I'm graphing this equation, I'm going to go ahead and start this. I know this is a quadratic that starts at 1, goes up 1 over 1, up 3 over 1, and there's my quadratic. But I only want to graph it from x is less than 0, which means that this becomes an open dot, and I only graph the left-hand side of it. So I'm going to come back and I'm going to erase what I didn't want, and I'm done there. So now for the other side, I'm going to graph, this, the x minus 1, which is a line that starts at negative 1 and goes up 1 over 1. And so now if I wanted to evaluate my function when x is negative 1, then really all I'm doing is, okay, what's f at negative 1? And I have two ways. I can look at my graph. Well, what is my value when x is negative 1? Well, it's this piece of the graph because negative 1 is only graphed on the blue graph. And when I look here, that makes sense because negative 1 is less than 0. So that means that algebraically, I'm plugging in negative 1 into the top equation, not the bottom. And so this gives me 1 plus 1, which is 2. Does that match my point? Yeah. At negative 1, my y value is 2. So now I can go ahead and I can do f of 0. So then I'm looking at, well, whoa, I've got two different things going on. I've got an open dot here and a closed dot here. Which one applies? Well, it's the closed dot, because closed dot means that we include it, open dot means we do not include it. How does that compare to over here? Well, 0 is not less than 0, but 0 is greater than or equal to 0. So this is the equation we would use. So if I'm plugging in, I plug into the second equation because that's what fits my domain restrictions. I don't know why I just put a comma there. So this would actually be negative 1. And then our very last part, which is f at 1. And since 1 is greater than or equal to 0, we plug into here. So this would be 1 minus 1, which is 0. And I could even check at my graph. At positive 1 for x, my y value is 0. So the last part I wanted to talk about is implied domain of a function. And the implied domain of a function is kind of logistically thinking through, are there any numbers I cannot plug in for x? Or can I plug in every number I want for x? And so when we look at a problem like f of x equals the square root of x, I think about, can I square root every number, or are there certain numbers I cannot square root? And there are certain numbers I cannot square root. I cannot square root negatives, I can square root 0, and I can square root positive numbers. So here, my x value cannot be negative. But it can be 0, and it can be positive, which means my x will have to be greater than or equal to 0. It can be 0, and it can be every number bigger than 0 because those are my positive numbers. But it can't be negative, and those numbers are the ones that are less than 0. So this is my domain. Now what would that domain look like if I wrote it in interval notation? Well, I include the 0, so my lowest value that I can plug into x is 0, and then any positive number all the way up to forever, which is infinity, those will work in there. So x is greater than or equal to 0, or in interval notation, from 0 all the way up to infinity, all those numbers would work. So in my sample problem here, find the domain of each function. Well, domain is my input, it's my x values, so my domain would consist of all of these values. Now you notice that I have two twos, so the 0, 2, and 0, 2. So it is a function because it's the exact same point. But just because I have two zeros listed does not mean I list them twice. So my domain consists of only points, so only the x values, -3, -1, 0, 2, and 4. That is my only domain, because I don't know if these dots are connected or if they're just dots. So that's the only thing I can assume. So my next one, g of x equals -x squared plus 4x plus 5. So I know right away that this is a parabola. I know it opens down because it's negative. And I ask myself, is there any number that I just can't plug in? Can I square every single number possible? I'm pretty sure I can square anything. So that'll work, and I'm pretty sure I can plug any number in for x here. And when I think about the graph, and I think about domain is my x values, and x values go side to side, right? X-axis. And when I think about my graph, does my graph go side to side forever? And it does. Every parabola kind of goes over and down, well, this one goes over and down, or over and up and over and up and over and up. And it keeps going out forever, which means this is all real numbers. How that looks like in interval notation, -infinity to infinity. All numbers you can think of that are real, you can plug in there. Now our last one is a little trickier because you think, oh, I can plug anything I want in for x, except for you forget that there's one number you're not allowed to divide by. And you're not allowed to divide by the number 0, which means that this on the bottom cannot be 0. So if I were to manipulate this and subtract 5 from both sides, I end up with x cannot equal -5, which makes sense when I look at it because -5 plus 5 would give me that 0 on the bottom, and that's not allowed. We're not allowed to divide by 0. And so that's what we're talking about in a lot of our stuff today. Okay, next one, volume of a sphere. So the equation is volume equals 4/3 pi r cubed. Is there a certain number I cannot plug in? Well, when I think about it, I can cube any number I want. But the problem is the situation. Is there any time where I'm going to have a negative radius for a sphere? There is no time. And is there any time that I'm going to have a sphere that has a 0 radius? No, because it's not going to exist. So technically, our radius will have to be greater than 0. And that would be our domain. And it's not our domain for the equation, it's the domain for the situation. I will not have a sphere with a radius of 0 because then it's not a sphere. I will not have a sphere that has a negative radius because then it's not a sphere. And so based on our situation, so this is a situational domain where r is greater than 0. Okay, and then our last one, kind of going back to square root, I cannot square root a negative number, which means this cannot be negative. So 4 minus 3x has to be greater than or equal to 0. And I could solve that to get my actual domain. So if I minus 4 from both sides, I end up with this. If I divide by -3, because it's an inequality, when I divide, my sign has to flip, and I get x is less than or equal to 4/3. And that is my answer. So this is your assignment for day 1, and I wish you the best of luck, and come back in with those questions so we can talk about them.